Next, we will consider a situation where our body has constant density. Now, if we divide mass by density, we are left with volume, for our mass is equal to our density times our volume. And our volume is equal to integral with respect to our differential volume. Now, our first moments of mass can then be divided by density such that we can determine our center of volume. That is, x bar would be equal to 1 per the total volume of our system times the integral of x with respect to our differential volume. Y bar is equal to 1 per the total volume of our system times the integral of y dv. And lastly, z bar is equal to 1 per our volume times the integral of z dv. In example 3, we want to determine y bar for our paraboloid. And we are going to use the method of disks. Now, our paraboloid is given by a function z squared is equal to 100y, where the bounds of y is between 0 and 100 millimeters, and our paraboloid has a diameter at a maximum of 200 millimeters. For this problem, we are going to ignore significant digits. Now, for us to begin, we are trying to determine y bar. So we are going to construct a differential disk with a thickness dy and a radius r is equal to z. And this differential disk is going to have a differential volume dv. Now, since r is equal to z, i.e. r changes as a function of y, our differential volume is expressed as pi z squared dy. Thus, we'd have y bar being equal to the volumetric integral of y dv per the volumetric integral of dv. Now, this would be equal to integral from 0 to 100 of y pi z squared dy. Now, we note that z squared is equal to 100y, so we can substitute that expression in. In our denominator, we have the integral from 0 to 100 of pi z squared dy. This would be equal to 100 pi times the integral from 0 to 100 of y squared dy per 100 pi times the integral from 0 to 100 of y dy. And after integration, this would be equal to 2/3 y evaluated between 0 and 100 millimeters. Thus, y bar would be equal to 66.6 repeating millimeters. Method of shells is slightly different. To construct a shell, we are going to revolve a differential area around our y-axis by some radius r. Now, r exists in our z direction, and our differential area can be expressed as dz, our thickness, times our base, and our base is 100 minus y. Thus, the differential volume of the cylinder constructed by revolving dA around our y-axis is 2 pi r dA. This is equal to 2 pi z, recalling r is equal to z. Our basal length of our differential area is 100 minus y, and we're going to multiply this by dz, our thickness. The center of our differential area is going to be y plus 100 minus y per 2. This is equal to 100 plus y per 2. This is giving the center of our differential area away from our origin. Now, y bar is equal to integral with respect to our volume of y dv per the integral with respect to volume of dv. If we populate the numerator, we have the integral from 0 to 100 of y, which is expressed as 100 plus y per 2, times 2 pi z times the quantity 100 minus y dz. And this is per the integral from 0 to 100 of 2 pi z times the quantity 100 minus y dz. This is equal to pi times the integral of 0 to 100 z times the quantity 10 to the 4th minus y squared dz per 2 pi times the integral of 0 to 100 z times the quantity 100 minus y dz. Now, we recall z squared is equal to 100y, which defines our paraboloid. We can solve for y. Y is equal to z squared per 100. And we can make the substitution in for our y terms. Thus, in our numerator, we have pi times the integral of 0 to 100, z times the quantity 10 to the 4th, minus the quantity z squared per 100 squared. And this is integrated with respect to dz. In our denominator, we have 2 pi times the integral from 0 to 100 of z times the quantity 100 minus z squared per 100. And this is integrated with respect to dz. Thus, after integration, we'd have y bar is equal to 2/3 z evaluated between 0 and 100. And thus, y bar is equal to 66.6 repeating millimeters, the same as we got via method of disks.